Okay, so today we continue with these Lebesgue measurable functions. So, does anybody of you remember the definition? Actually, in this theory, the main thing are really the definition.
If you also see
So, F is measurable, and we will use for shortness the notation L0 if
The inverse image of each Lebesgue.
f to the minus 1 of intervals. They have several definitions. Intervals, well, open sets from half lines, intervals, open sets, then Borel sets. No? Okay, so let's take that stuff. One, we're going to see plus infinity. And okay, we can assume even that it gets plus infinity set, doesn't matter. Belongs to the measurable sets. Okay, and then we know all this. But okay, there are several definitions, several equivalent definitions.
Is that correct?
Why you don't like that?
It's the inverse image of each Lebesgue measurable set. Is
Yep.
Lebesgue measurable?
Yeah, this is Lebesgue measurable.
Yeah. No. There. We took only the interval. It's division.
For all C. Yeah.
This not give us just that it is Borel measurable.
No, because this is the sigma as well Lebesgue.
No, but I thought that definition is that the inverse image of each Lebesgue measurable set.
No,
is
that
measurable.
cannot be.
That's not true. What?
That's not true.
No, the
we have-
definition. I am talking about definition. I thought that
Definition. The inverse image of well, the largest one is the inverse image of Borel is
is the
Lebesgue.
measurable.
yeah,
Okay.
because the inverse image of Lebesgue,
Yeah. Is not
unless you have a Lipschitz function,
yeah.
then it is
Then
not.
it's the, yeah. No. If it's I mean if it's Lipschitz, then it assumes what I said, right?
If it's Lipschitz, okay, because Lebesgue set of measure 0 are mapped into set of measure 0.
Yeah.
The inverse is Lipschitz.
Yeah.
Yeah. But we have an
I
example
thought
that
that's the definition of Lebesgue measurable in general.
no, because okay.
You want a discontinuous map to be measurable.
Yeah, but well, this is the inverse, so it can be discontinuous, but the inverse should be Lipschitz. If you want the inverse should be Lipschitz, because you want to have Lebesgue set of measure 0, they are mapped into set of measure 0s, otherwise you have the trouble that sets which are measure 0, which are measurable, clearly, are mapped into sets which are non-measurable. We have that example, not the Vitali function plus x to the measure. That was the that example, no? So that is a function which is continuous, but is not Lebesgue. In your definition, is not the Lebesgue measurable because there is a set which is a subset of the Cantor set.
Yeah, so how we call these functions? Because I remember that I studied them. This function that maps the Lebesgue sigma algebra to the Lebesgue sigma algebra. What's called this kind of function?
This I don't know, but it's not the Lebesgue measurable function.
Ah, okay.
And it's a very restricted class.
Yeah, because
It's a function which maps set of measure 0 into set of measure 0.
Yeah.
That's the property you have to require.
yeah. And
So
now-
the inverse.
Yeah,
Set of
because-
measure 0 measure 0.
Yes, because when we studied measure theory, we studied it like in a very general case. sigma algebra measure, sigma algebra measure.
Okay, yes.
When we said that a function is measurable, isn't only if each element of this sigma algebra is in this
Yeah.
sigma algebra.
Yeah,
So-
and here is the Borel to the Lebesgue.
From the Lebesgue to the Borel.
You have Lebesgue here and Borel here, so the inverse of Borel is Lebesgue.
Okay, okay.
Because
So they are not both with Lebesgue.
No, no, no.
Okay.
But because for the integral, you need just to compute
Yeah.
you remember, for simple sets,
Yeah.
so simple functions, which are just characteristic functions, okay, you need to have the inverse, so which is equivalent to the set where is non-zero, or the set where is zero, which is the opposite, are Lebesgue, in order to give a value to that area.
Okay.
So that's enough. So because you need to have the smallest sigma algebra here, well, actually, you need to have the smallest sets such that you can compute the integral and discover at least the intervals. And then you discover that, okay, since it is a sigma algebra, I can extend to a sigma algebra, but no more. If you require too much on the left-hand side, so you restrict the class of functions, and that's not what you want. You want to integrate as many functions as you can. Okay, so now, so the definition is fine, but clearly we want to have well, the question was exactly how the largest class of function we want. So for example, if we have to prove that following theorem that if f and g are measurable, then, well, at least it is an algebra of functions, so the sum and the product and the scalar product is fine. Then, for all alpha, beta in R, alpha f, u beta, g is in L0, and also the product, f, g is in L0. And then the last point is the composition. Okay, if f is Borel, and this is the definition that the inverse of Borel is Borel, then f composed G is Lebesgue. So let's start with point 1.
Please, where f and g give
yeah, there is a problem, yes, of course. That T should be defined, so let's say they are real. So, and finite almost everything. Yeah, you're right, because otherwise there is the indefinite sum. Or you have to assume that, okay, when it is 1 is plus infinity, alpha is positive or negative, this one is positive or negative, so the sign corresponds. You don't have any undefined, so the sum should be defined, let's say pointless. Okay, so proof. Proof is the same for many of these theorems, and we will see later, for example, limits. So you have to write exactly this definition. So can you compute this set? So compute or write f to the minus 1 alpha f plus g plus, let's say, let's split because, okay, this is too much. Let's compute with an intermediate step. If f is measurable and alpha is a real number, then alpha f is measurable. Okay, so compute, so let's say this is step 0. Compute alpha f to the minus 1 c plus infinity. Okay, this is easy, no? So, which are the point x such that alpha f is greater than c? Let's say alpha positive, for example.
Otherwise, it's really annoying.
Yeah, otherwise, okay. Let's say for alpha, or we have, if alpha is greater than 0, I hope that I'm not there, then in this case is the set where f is larger than c over alpha. Okay, doesn't matter, yeah. And if alpha is negative, okay, then f is less than c over alpha. And finally, okay, if alpha is equal to 0, leave this mess. 0 doesn't matter. It's r if alpha is equal to 0. Oh, well, it doesn't matter. It's whatever. Alpha is equal to 0. Let's say alpha different from 0. Otherwise, it's 3. Okay. Second. So since we have already alpha f, beta g, we have just to compute f plus g to the minus 1 c plus infinity. Okay, let's assume they're finite, so let's say plus infinity here, because this, otherwise there is always the problem. But okay, equal. So we have to write the expression saying that are the x, y such that the sum of the two functions are larger than c. Okay, so let's start. Well, this means that f, let's say, if g is larger than a number, let's put a number here, so let's say h, then f should be larger than c minus h. Okay. So this is well, actually larger or equal, doesn't matter, even like this.
For all h. H can be rational.
For all h. Yes, for all h. So I am in some trouble here because h is an company. And then what I do?
We can
choose rational numbers. So for all h, so for all becomes the union over h in q. And the wedge becomes the intersection. So it's f to, so this is g to the minus 1 of h plus infinity, intersection f to the minus 1 of c minus h plus infinity. But it doesn't matter if I take that clause or not, because being the rational number and this is larger than, certainly there is even the equality. I choose a smaller h, then it's fine. Whatever. Okay, and now it's done. Being a sigma algebra is closed under those two operations. Product, that's all. So, and now, okay, there is a smart trick there, but I can do even, so you can do by exercise using the same tool, no? So if this is larger than c, and then assume, okay, take the positive part in order to divide it, should be h greater than h, with h positive and f larger than c over h. And again, take the irrational and do the same. Or, well, in the book, you just observe the following, that fg is equal to 1/2
square f plus g.
Yeah. F plus g square, sorry, 1/4 then, minus f minus g squared. And now, so you have only to prove that, so only to prove a particular case of this guy, which is that f squared is in L0. No. Because I know already these are in L0, so I have only to apply, the only difference is the multiplication by, sorry, the square. Okay, and this is a particular number of this guy because clearly the parabola is continuous, so it's a Borel function. Okay, well, and now again I just apply the definition. So f squared is larger than c when, but this is the union where, okay, I should be careful about, but let's say c positive, c negative, always c positive, I take the square root, f larger than square root of c, and then the union f smaller than square root of c minus root of c. So okay, this is so the only thing in my this proof is the fact that, well, you use the rational number, so this is the smartest point to avoid taking infinite, uncountable union. You just use the rational number. And this is really the property of the real numbers, no? They are defined by the closure of a countable set. And now, this study is very important because you see, once you have this guy, essentially all the functions you can build, which are by sum, multiplication, and then composition, they are fine. Then later with limits, and at this point it means that all the functions you can really construct or imagine they are measured. Okay. So let's see. Let's compute f composite g to the -1, and now it's better to use of a Borel set. So let's say of a Borel. And B is in the Borel sequence. Is equal to what? So by definition, it means that G should belong to the counter image of B by F, no? So this is G to the -1 of F to the -1 of B. And being a Borel function, this is still Borel. And then being this in L0, this is in L0. We know by the example that this composition rule does not hold when f is just Lebesgue measure. So one have to be careful making compositions with Lebesgue measurable functions. So only the last one can be Lebesgue measure. The remaining one cannot be. However, of course, there is the question that, well, there is the standard observation that if you don't use the axiom of choice, basically you are fine with all the operation you can do. Okay, so that's the thing. Okay, so let's go on with the. I think I went too much on the right. Proposition. This is almost an exercise. So F, G are measurable, then the minimum. So and let's say and finite. Let's say and finite almost everywhere. When it is plus infinity, you consider that set on your well, you consider the set as a particular case. No? So the real thing is when it's finite. So the minimum of f, g, the maximum of f, g, and there is something else, no, are measured. But this is an exercise, no? Because the minimum
can be expressed as f plus g with, we can write it as the, we can write that the maximum is f plus g minus the absolute value of f minus g over 2.
Ah, yeah, we can use also the composition, yeah.
So using the what?
Yeah. Or well, here you can really write, I will write directly this one instead, because the minimum, when is so the minimum fg larger than c is the intersection. And the max, which is the same, is the union. Okay. But yes, since we have the absolute value, we can use also the absolute value. So And then corollary. Well, we know the but actually this one is also corollary of this guy, no? The F plus, which is the positive part, F minus, which is the positive of the negative part, and the modulus of F are measurable, which is just the composition. This one, okay, you can write directly, or this one is the composition with the function, which is the positive part of X. Okay, now let's see if there is some nice exercise. Okay, let's do something which will be in the next exercise, just to see. So let's say Fn is a sequence of L0 functions. Prove that the set E, which are all the x such that there exists the limit of Fn of x, the pointwise limit. Okay, this is measurable. Okay. So this exercise is nice because it's the method that you are going to use for proving the limit of functions are measurable or not. So the idea is that I have to rewrite this condition here as countable union or countable intersection of sets. And then, since everything will be measurable, I'm fine. Okay, so let's rewrite this condition here. So what does it mean that the limit exists? So, does anybody has an idea?
Where are the definition that for all epsilon there is some range?
For all epsilon, so if x is in E, then for all epsilon
there is some range and there
exists some range.
N.
Some n, okay.
Such that for all integers are equal than n.
Okay.
Absolute value f of n x.
You don't have still fx, no? Well, okay, yes, fx or because you don't. If you use fx, you have a trouble. You don't know if fx is measured.
Yeah.
You see, because then you're going to write that less than epsilon, and then you apply.
No, I mean sorry, not for all n, for all n and m. So we
okay.
use the Cauchy.
So for all, there exists n for all. Let's say there exists k. For all n and m greater or equal than k.
For f of n of x minus f of m of x. So
yes. Yeah. And now, translation. I need just to translate as I did for this thing or this thing, this logical proposition into set a set formula.
We have to change the sign by.
Okay, so this one is the set. So are all the x such that this guy is less than epsilon.
Take epsilon for one or
for all means intersection larger than k. There exists means the union. And now for all means intersection. And well, epsilon is however uncountable, so I prefer to write 1 or 2 to the minus I. Okay. So this is the set where the limit exists. Because for all points in this set, well, vice versa, it is just the translation. Okay, so it really measures. So you see that the even limits can be rewritten into conditions on sets. And since we can use the countable sequences in R to take limits, we are fine. And indeed, the next step is to compute, to prove that the limit of measurable function is measurable, which basically is written there, no? You see. So let's start with some definition. Fn converges to f pointers. What does it mean? Okay, so far we assume that it's finite almost everywhere. We will not discuss plus infinity. The discussion of plus infinity is always like a particular case. If you want to have very general statement, you can put plus infinity, but clearly it's something you don't care. In general, you don't care. And if you care, okay, plus infinity is very easy. It's the easy case. Okay, what does it mean it converges pointwise? Okay, let's have a look. Fn converges to f. What's the second one? Almost everywhere. Well, let's say uniformly. And Fn converges to f almost Lebesgue almost everywhere. Okay, we have these three notions. Okay, let's start. Which is the strongest?
What is the last one?
Hmm?
What is the last one?
Almost everywhere. You remember?
Pointwise?
Pointwise, almost everywhere. Yes, almost everywhere. Usually I say almost everywhere. Okay, so uniform is the most stringent because is the super. So let's say that for all epsilon there exists let's say n, the supremum f minus fn. So for let's say there is k for all n larger than k, the supremum is less than epsilon. Okay, and this guy? Yeah, this guy goes on, comes out. So for all x and epsilon, there exists a k, which depends now on x and epsilon. For all n larger than k, f n minus f in that point is less than epsilon. And the last one is the pointwise up to a set of measure 0. This is the pointwise outside a set n, the measure of n is equal to 0. Now I take a question that it will be the end of this week. I think is a very important option. So I'm saying, do you believe that from the point of view of the measure, essentially these three convergences are basically equivalent? Okay, so I have to specify what does it mean basically. So do you, if I tell you, I'm the Lebesgue measure, for me they are all equal, almost equivalent.
Well, for A and C it's clear, but is B assumed always? That converges, uniform
yes, in this
converges
sense,
almost
no.
everywhere?
But I'm a measure, so I don't see, I can remove small sets, arbitrarily small sets. Yes. So if you allow me to remove sets of, very small sets, so which means that a measure arbitrarily small, then yes. So this is the end of the story. Ego, yes, this is ego of theorem. Yeah. And at the end, indeed, as I told you before, you don't. At the end, the functions you really construct are basically continuous, and the convergence is basically uniform. But one has also to use the correct language, no? Okay, so the proposition. Fn converges to F and they are in L0. And let's say, I think after this lesson, we will, all the F we have are in measure. Because still, this is the lesson where we prove that if all the operations that we usually do, and actually all the operations we can have in mind, they create measurable functions. Then F is in L0. Proof. Okay, the proof is already in the exercise. It's in the exercise. Simply now I know that the limit exists. Okay, so let's do it this way. I want to compute when F is larger than C.
Yes, this is the intersection of F and the of this, which is
Yeah, it was already in the exercise. You have to change a little bit, but it's already. But let's do for this. So when F is larger than C, what does it imply on Fn? So I fix C and I have a point X here and the value of F is larger than C. What does it imply on Fn? Fn converges. So we remove, so this is pointwise or almost everywhere. So we remove already the set where that does not converge. Okay, what happened for this limit? So what should Fn satisfy in order to have that F is larger than C?
converge to C. And over
To
There is some number after that.
Yeah,
higher than
C. Yeah.
Okay, so yes, so I write the sentence here. There exists K for all n larger than K, Fn should be larger than C. No? Now we have to translate. Okay, so this set is already okay. Now for all means intersection. There exists a union. There is only one problem.
Is this K depend on X?
No, because you know that for any x, at some point, so for any fixed k, for any x there exists a k. So at some point, this x belongs to its set. Well, it's correct. There is only, the other is another one. Is that if the value of f is equal to c,
If
the value of f is equal to c, and I have a sequence converging this way, is in that set. So okay, so I have to still do a piece.
I don't understand the problem, just
No.
So consider the function fn is equal to the minus n.
yeah.
And you want to say what is the set where f is larger than 0, which clearly is empty.
Yeah.
The limit is 0.
Which
But in that set,
Yeah.
this guy, so this guy, r is inside here, so you get r.
we should some epsilon to s. For example, 1 over n.
Here. So you have certainly that this is plus h, and then you union over h, and h, let's say so let's say 2 to the minus I and 2 and I. Yes, now it's There's a little bit of these tricks, but okay. But I think if you are able to reach this, you know how to fix the rest. Just an observation. Particular measurable functions, which are the fundamental bricks of the construction. Example or definition. Well, the example is the characteristic function. So the notation is I use, and indeed I'm not coherent here because characteristic function should be denoted by chi of A. 1 if x is in A, and 0 if x is not in A. And, but actually, somebody else says that this is the indicator function. Which is the indicator of A is the same definition. And then there is still another function which is so the complement of these two definitions is chi of A is equal to plus infinity 0 if x is in A, plus infinity x is not in A, and the complement of this guy, which is this guy. 0 x in A plus infinity x not in A. So, okay, so you have to choose, you can decide to switch as you want. You can say that this is this definition, that is becomes the other definition, and you call this guy characteristic and or indicator, and you call this guy indicator or characteristics. I found all definitions, all combinations in different books and papers. Okay, so which one you prefer? The key?
I prefer the one for the this for characteristic.
Okay, and as a name? Characteristic is the one inside, 0 outside.
No.
Okay. No.
No. Characteristic should be.
Okay, so let's do the following. One of you chooses the name and the other chooses the symbol, and for me it's fine.
I choose the first notation.
So this is chi, and then we cancel then the name. Oh, sorry, this was a different name. Is a ball. Characteristic. Okay, so that's characteristic. Done. Characteristic function. So when this function is measurable,
A.
yeah, of course, is equivalent to A. This function. Why is a building block? Because of the following definition. Let me write this here because it's very important. And I know that is not a definition. F is simple if simple function if F is the sum k equal to 1 to n of finitely many characteristic function with some constant form. Let's say ek, but okay, this is for general. Ek of x.
Do you have the joint or not?
Not necessarily.
F of x.
Hmm? Yeah. Okay, but your question, can you make a representation of this one as a disjoint?
Yeah.
Yeah, of course, you take the intersection, and in this intersection you sum up the constant c. And now the fundamental lemma. It is very elemental, but it's really the fundamental. And the important thing here is not really the statement, because from this you prove A growth and losing all the important theorems, but it's really the way. So memorize the way. Lemma. Let F, okay, from some, let's do in the simplest case, some intervals into R finite. Then, for all epsilon, there exists phi, psi simple functions such that the first property is that phi is less or equal than f less or equal than psi. The second property is that psi minus phi is less or equal than psi.
F is
Whatever. If clearly, if I'm not saying that these functions are measured. So it's just a method. If corollary, we see corollary f measurable, these functions are even measured. Okay, and for the proof, I will make a drawing and ask you to understand what I will do. So let's say this is f.
So we take equipartition
Well,
of the center.
well, here,
Yeah.
you are Riemann.
What?
You are Riemann. Riemann.
No.
Well,
I don't understand. What's the problem? I am going to define phi and c.
But when you say f is fine, you mean bounded?
What?
When you say f is fine,
Very
you
bounded,
mean
yes,
bounded?
sorry, bounded. Yeah, sorry. It's my fault. It's really bounded.
I mean, just the idea. I mean, not the. I mean, not the real axis only. We do a partition.
But which axis?
No, this one. Yeah.
This one, like this one?
Yeah.
This is Riemann.
But I am not going to integrate. I'm going just to define phi and
Yes,
and
but
see if it
okay.
works or not.
Okay, let's say f is the characteristic sorry, the characteristic of the real of Q.
Mm-hmm.
We will never get epsilon in the second point. So, well, you remember at the beginning, I told you, well, I think the integral, exactly, I slice horizontally. That's the trick. So let's slice horizontally. Which will be these sides?
the minimum.
What's this guy here? Epsilon. So it's almost right. You just have to rotate 90 degrees. Epsilon. So let's slice by epsilon. Okay. Let's build the simple function. So at least let's start with the one below. Okay, the one below I draw it. Will be this one. Okay, so we need just to give the definition now. So phi of x is equal to, okay, this is 0 and let's say the height is m. Or let's say this is, so this point is k epsilon. So it's equal to k epsilon if f of x is in
K epsilon, K plus 1 epsilon.
Okay, now we have to decide which one to close, because we want to have something which are disjoint, no? So let's close this guy. So let's say k epsilon, k plus 1 epsilon. And I have finitely many values because of being bounded. Okay, if it go below, it's still bounded. Are you fine with this definition? So you take the x and you say, okay, I take the set where f is in this interval, and I give the bottom, the lower value.
Yeah, by definition, f is higher.
Is defined. And now what will be psi? So psi clearly is the other one. So it's like phi of minus f in some sense. Minus phi of minus f. Okay, so I just draw it just to be sure. Okay, whatever. This is a little bit sticky. So psi of x is equal to
K plus
k plus 1. The function are defined. Is it true that f is in between? Yeah. Is it true that the difference is epsilon? Yes. So now, since we have to show that Riemann was very smart, but here Lebesgue was smarter. So if f is the indicator function of the rational number, which will be phi and psi?
1 and 0.
No?
Ah, 1 and 1. Yes. Hmm?
It's f. It's already a simple function. But clearly I can change the values a little bit, no?
No, but the definition of simple function is finite.
Yeah, it is very
It's
smart.
finite. I'm not saying that A are intervals.
Oh, yeah.
That's the difference of the.
Yes.
So you remember, indeed. So let's jump a little bit further now. So now, how to compute an approximate integral of f here?
Calculating phi and
The integral of phi. And what is the integral of phi? If phi has this form.
is the sum of ck times the measure of
Yes. So this is you see the difference, no? The Riemann integral was exactly, I slice vertically and I give a value of f there and I add this rectangle. Here I have the power of the Lebesgue measure, which is able to give values to very large class of sets. So I just slice horizontally, and so let's say vertically is very easy. I do the sum. The complication is in the horizontal part, because I have to compute the measure of sets, which are very complicated. But I already constructed this function. Let's go on. So this is really, so you have to imagine, okay. Here, let's f. Now we remove all the things. It's not in an interval and it's not just bounded. F is in a 0, then there exists a sequence of phi n simple and in a 0 measurable, such that phi n converges to f and phi n is bounded. So the difference between the two statements, until you want to see that the second statement is much more complete, but actually instead is the real statement is this one. You have to think about that picture a lot, digest it, because it's the fundamental idea. This is my opinion. So the only thing about the difference from lemma to theorem is that I have to reduce the theorem to the lemma. That's it. So, well, we can keep away the interval, or well, instead of the interval we have a general set, and we can take away the boundedness. So proof. Let's do some steps. First of all, can I restrict to positive and negative? So I can restrict to the set f greater or equal than 0 and f less than 0. Simply because if I have simple functions and I intersect with two sets, it's still a simple function. Now, instead of having a here, I take a intersection when f is larger than 0, and a intersection when a is less than 0. The measurability is preserved because the singularity is closed, and that's it. So I have only for f larger or equal than 0. Just for simplicity. Second, I want to restrict, so the construction of the lemma, I really need to have the boundedness. So what I do? Well, at some point where m is too large, I just cut it. Okay? So define phi is equal to, let's say, phi m, or let's say phi n is equal to the as lemma, as in the lemma, with epsilon equal to the minus n, in the set f less than 2 to the n. So I restrict to the set 2 to the n, I redo the construction, so the definition is exactly the same. Instead of epsilon, I take, since I want an index n, I take 2 to the minus n. 1 over n, doesn't matter. The only thing, one should go to plus infinity with n, and one should go to 0. And now what I say is 2 to the n if in f larger than 2 to the n. So when it's larger, I say that it's 2 to the n. Otherwise, I slice it and define a simple function. Okay. Is it true that it's converging? Yes, because from this guy, you say that phi n minus f is less than the epsilon, which is 2 to the minus n, in the points where it is finite. In the points where it is plus infinity, this is going to diverge. But okay, it's plus infinity. And there is one point still here that is the measurability. Here. Okay, why the function that I construct here is measurable? Which one? This function here. Yeah. So this is measurable. Let's look at the construction here. The construction here gives that the set where ST's value is a measurable set. Okay. Okay, now let's see. Okay, there are many variations about this principle of approximation. I think you will see with the tutor. Let's do a little bit further. Okay, so much nicer. So I finished today with the following image. So two very important theorems here. So okay, the book presents like three principles, which were little, but I don't know. So let's see. So in the book you have these three principles. And my impression is that yes, they are very nice because in some sense these are the tool. I mean, how to say something not really formal, an informal way of memorizing the basic properties of measurement. So the first one is that if E is measurable, then E is essentially the union, finite union of intervals. We already seen this property, no? And why is that so? Because if E is measurable, you remember, by definition of Lebesgue measure, which is the outer measure restricted, there exists a family of open set shrinking such that the limiting measure is the measure of that set. So at some point you have one open set whose measure differs of, let's say there exists open such that the measure of open minus E, so open containing E, and this is less than epsilon, for all epsilon, remember, no? But our open set essentially are union of this joint interval, countably many. So you can take finitely many such that the difference is less than 2 epsilon. The second one is that you have a function, and notice that the losing is a function. If a function is in L0, then f is almost continuous. Which is so strange because the indicative function of the rational number is almost continuous. And now is the Diegorov, which is that if fn converges to f and they are measurable, then, okay, in a set of finite measures, but we will see later that, then fn converges to f almost uniformly. This almost means that you remove a bad set, but this bad set is a measure which can be made arbitrarily small. Yeah, it seems strange. So let's, so the proof of the second is given by the proof of the third one. So this almost means always you remove a small set. So example. The indicator function, the characteristic function of the rational number. Okay, so let's see the first. Rational number. So let's do the rational number. The set of rational number is so. What is a finite union of the joint sets such that essentially their symmetric difference is as small as you want? They are equivalent to this joint union of finitely many sets. This is easy because the measure is 0. Okay, so the Lebesgue measure of first principle, the Lebesgue measure of Q is equal to 0, then there exists a finite covering, E covering, such that the sum of the length is less than epsilon, for all epsilon. So in particular, I take finitely many of these sets. So Q essentially is a countable union of these sets. And I have the measure of the different symmetric difference is less than 2 epsilon, let's say. So it's actually less than epsilon. This is a particular case. Okay, so this is the meaning of the first statement. Essentially, Q is an open set of very small measure. So it's nice. So I want to apply the second one to the indicator function of Q. So the meaning almost continuous means that if you remove a set of a small measure, then it is continuous. Here is very easy. Exactly. So is equal to 0 up to Q, which is a set of measure of Q, is equal to 0. And this function clearly is continuous. 0 is a continuous function. And now, okay, let's think how to do the Egorov. Okay, I define Fn of x is equal. Okay, let's say that Qn is a numeration of Q, being countable. There exists an enumeration of Q, and so this is 1 if x is in Q1 up to Qn and 0 outside. Otherwise. So is Fn converging to the indicator function, the characteristic function of Q? Pointwise. For any x, either is irrational, then it's always 0. If it is irrational, there exists an n such that at this point is equal to 1 from that n for onward. So Egorov means that you remove a set of arbitrarily small measures, the convergence is uniform. Which set you remove is always the same. Here, there is only one set. Clearly, Fn compared to, sorry, this is the characteristic function. The characteristic function of Q uniformly in R minus Q. But it's almost trivial. But you see that even a function which seems quite bad actually is not that bad. So this is the meaning of the principle. Are you okay with this? More or less. It seems strange, but then you have to digest it. So. Okay. So I stated in this way, and apart the first, the second follows from the second from the third. So the real key point is the third one. So let's prove the third one. I cancel this example. Egorov. Let E measurable set, measure of E less than plus infinity, and Fn a sequence of Lebesgue measurable functions such that Fn converges to F. Okay, I can say almost everywhere, but let's say pointwise. here almost everywhere or almost everywhere, doesn't matter because you have always to remove a small set. So almost everywhere remove this set from M, E, and then here still pointless. Then for all epsilon there exists a compact set compact such that the measure of E minus K is less than epsilon and Fn converges to F uniformly in K. So I have a question for you. Previously, in our example, we gave a set which is non-compact. You remember, I say the irrational number is the set where it converges uniformly, which is non-compact. Do you believe that the compactness here is fundamental, or is just yes? Okay, it is just obvious from the Lebesgue theory, the Lebesgue measure theory. So I'm saying the requirement that the set of uniformly convergence is compact is one of the key points of the theorem, or it's just I can replace it with something else and then the statement will be the same.
Finite.
Yes, why? Remember, set is measured if there exists a family of closed sets converging from inside.
Yeah. Okay. There's limit of compacts at the end.
Yes, and then, okay, it's a limit of compact set because we have another statement that tells you that if a set, well, a set is a countable union of set with finite measure. And here, the assumption that the measure is finite says that the compact sets are finite. So in our example is not really something, so we are not requiring more. It's trivial that we have a compact set. We are understanding. Okay, and then the second question is how to approach a theorem like this one. How to approach a theorem like this one? I'm asking this because one says that, well, I don't know, but actually we already did it.
What we did before in physics?
We did before to write the limits as well, in set notation.
Yeah.
So now I'm asking you to rewrite the uniform convergence condition using intersection union.
It's the same, but just the union, the intermediate union becomes an intersection.
Pardon? I have the uniform, no?
Yeah.
Okay, so we define, so okay, I want to write the uniform convergence. Let's write the uniform convergence and see if we can define. So the uniform convergence means that for all epsilon, there exists K, not capital K like this one, sorry. For all n larger than K, and for all x now in the set that I need to consider here, Fn of x minus f of x, and now I have no trouble because I know already that the limit, I assume the limit exists and I know it's measurable. So when I will write the condition this guy, I get measurable sets, less than epsilon. Okay, so the starting point is I rewrite my condition and translate it. Let's translate it.
Intersection over epsilon.
Okay, take this set here, no? First set.
An intersection over x in K.
Okay. And now I define that this set, just because This set, let's call it E k epsilon. These are the set such that from some index onward, the distance of Fn to F is less than epsilon. So I translated these to, sorry, these things. And now the thing, k depends on epsilon. So the problem is that if you see, k depends on epsilon. If I'm not careful, I get 0 because I have to specify the dependence of k from epsilon. You give me epsilon, I give you k. So this is a function. And the function is unknown. So I have now to construct the function. And the trick is that, so the observation, of course, this observation is the key point, is that let's send k to plus infinity. When k tends to plus infinity, converges to, so when k goes to plus infinity means all the points such that they are inside epsilon in the sequence. So because we did not use that this pointer is convergent. So if it is pointer at convergent for any x, there exists a k. Okay? Okay, let's do it. So take this set. Take this quantity here with x fixed. I'm saying that when k goes to plus infinity, every x satisfies this condition from n larger than k. Because this is the pointwise limit. So my pointwise limit means that, so let's say this converges to E because for every x there exists a k such that for all n larger than k, fn of x minus fx is less than epsilon. So every x at some point enter in one of these ek epsilon when k is sufficiently large. You give me x, I give you a k such that is inside the set. Do you agree? You don't agree? You agree? You don't agree? Well, now properties of the measure. So you see, the k is increasing, no? Because if I take a larger k, I intersect in less sets. And it converges to it. Property of the measure. Then, since m of e is less than plus infinity, well, it doesn't matter, this doesn't matter. Then, the limit over k of the measure of e k epsilon is equal to the measure of e. So now what I have to handle is to be sure that, well, I would like now what to do what? To intersect this k with respect to epsilon, the sequence of epsilon. But I want to be sure that this intersection is non-empty. So what I do is that I take, so this implies for all epsilon, okay, for all, signifies that for all I, there exists a k, so the limit is this guy, by definition, such that the measure of e k epsilon, let's say ki, is larger than the measure of e minus, oh, well, okay, here I can put say for all the, because then I'm going to add them, let's say, the delta 2 to the minus I. Unfortunately, I did a mistake because there is an epsilon here and the same epsilon here, but these are two different quantities. Okay, we will see it. So this is the definition of the limit. Because limit, this is less than this guy, and being the limit is larger. So I can choose, and this is the function k. This is the function k that I choose depending on the epsilon. Okay, so I can say that if I take k sufficiently large, and k depends on the epsilon and this I here, I need to remove just a set of small measure, and for the rest, this is a large. These are now a large set. So at this point, I can intersect everything with that guy. So final formula. So that epsilon, so I replace this epsilon with 2 to the minus j. For all j, there exists a k which depends on j and, well, I can use the same j, let's say. For all n larger than kj, sorry, let's say, yes. Okay, let's n minus f of x is less than epsilon is equivalent to, if I take that k over here, is that for all j, there exists a kj such that the set, the measure of the set, where fn of x minus fx for all less than, sorry, epsilon becomes 2 to the minus j. 2 to the minus j for all n larger than kj. And this set here is my A, kj, 2 to the minus j, as measure larger than the measure of E minus delta 2 to the minus j. Sorry, the formula is complicated, but let me redo it again. So, I want this set to be large. And I can do that because I know that they converge to E. So now what I do? I choose a sequence of distances which converge to 0. I need countably many because I want to do some countable operation. And this sequence is 2 to the minus j. I want to choose k sufficiently large in order to be sure that the set where from that index there is some index onward, from that index onward, the distance is less than my quantity, as a measure which is the measure almost all set minus something small. So finally set k, well, which is, well, should be, I can take this set even closed. Is the intersection over j e kj 2 to the minus j. Okay, so I reach a closed set, compact set, because okay, I can make them compact, let's say, sorry. I don't want to spend some time in the compact part, but the important thing is this form. So what happens in the intersection? Let's start about the measure of the intersection. The measure of the intersection is larger than, well, is larger than the measure of the sum of the measure of the what I left out at each step. So it's the measure of E minus the sum delta 2 to the minus j for all j, which is measure of E minus delta. because at each step, so the measure of the intersection is the total measure minus the measure of the complementary. The sum of the complements is delta, 2 to the minus j here, and so the sum becomes delta. And now what happens in K? In K, by definition, give me a smallest parameter, so which essentially is j. I'm sure that by definition, since K is contained in the set Kj, it implies that from there exists this Kj index, such that for every n larger, I have the uniform. The distance is uniform bound. So I'm not very. So I really try to prove it. I'm not very fond in the way I presented the proof. So if you want, we restart again. Want me to restart? Maybe you get confused because I tried to let you understand why the ingredients fit into that position. No? Not just I can write immediately for all j, write this guy here and prove that the convergence. Okay, so now let's do the straight way. Straight way is defined, is set here. Defined K J is the set of x such that Fn of x minus f of x is less than 2 to the minus j for all n larger than k, which is that set down there. Now what I do is that I observe the EKJ increases to E as k tends to plus infinity by pointwise convergence. Okay, by pointwise convergence, then it means that there exists a k which depends on j such that the measure of ke to the kj, let's say e minus ekjj is less than delta 2 to the minus j. And this was this step here. Let's say A is equal to the intersection over J of these sets E, Kj, J, and K contained in E compact such that the measure of A minus K is less than delta. This K makes the trick. So this is the proof. The solution. It's a little bit straight. Well, the proof is straight, but you don't understand why the pieces are in every place. So I prefer that you, but okay, this is as you feel things. I prefer that you may forget the proof, but you remember that, well, I have to rewrite this uniform thing. Well, this is has been already written, because we did already for the limit. And the observation is that when k goes to infinity, this guy converges to E. And since it has finite measure, I'm sure I can take that the distance is less than delta 2 to the minus j. And then now the intersection of these sets, so this function kj is the function for the uniform convergence. Give me epsilon, I give you the index k, which depends on epsilon. Here I give me j, I give you the kj, such that the distance will be 2 to the minus j. Yeah. Okay, I let you think. So you, well, one has to digest things. One is impossible to. Questions? So let me stop this.